Hello, everybody. Welcome back. Remember that last time we got to know the mathematical underpinnings of the advanced encryption standard, namely how math works in prime fields and extension fields. We also called them with a more fancy name Galois fields. And I hope you guys had a chance to look up the life of Galois because he is that crazy intelligent French guy who was also really crazy. So, a very interesting story. This is a long lecture. So, what we are going to do in this first part is we are going to give you some history in the introduction to AES. Then we're going to look into the main structure of AES. And then we are going to cover encryption. So, and in the second part, we are going to cover what is called the key schedule and the decryption. So those two topics here are in the second part of the lecture. So you will wonder what the key schedule is. Actually, we would only need encryption and decryption normally, of course, yes. But the key schedule is the way of AES how to generate a much longer set of subkeys out of one given key. So that's the purpose of the key schedule. And you need a whole lot of set of keys because we have a whole lot of different rounds, what it is called rounds in AES, and rounds are sets of actions that you apply to the state, which is the current state of the encrypted data over and over again. So let me give you some history about AES. Unlike DES, which was the established standard for encryption for a long time, DES has been developed by IBM, and that was kind of secret. So DES fell out of favor a number of years ago when it turned out that the computational power of nowadays computers has become so big that DES became insecure. So DES was augmented, and instead of running one round of DES, there was a version of it called 3DES. So you would run 3 rounds of DES, which made it again very secure. But the downside was that the computational costs were just too high, way too high, as opposed to AES, which is computational very cheap in comparison. And these days, AES has actually support built in hardware by modern processors. Okay, so in 1997, the National Institute of Standards and Technology made a public call for proposals for the soon to be coming up advanced encryption standard. So in 1998, 15 proposals came in. And you will wonder why 15 only? Well, it seems like back then cryptography was not as established a field as it is these days. So in 1999, there were 5 finalist algorithms. And in 2000, October 2000, eventually the winner was announced, which was Rheindal. Rheindal was chosen, and this was a kind of a surprise. It was the algorithm proposed by 2 guys from Belgium. You see the names here. Belgium is a tiny little country in Europe, and of course, it boosted, you know, those two guys' confidence as well as they were very proud of that, you know, as the small nation that they are. So Rheindal is the name that was originally given to that algorithm, and nowadays, you know, it's called AES, the Advanced Encryption Standard. Okay, what's the high-level view of AES? AES is a block cipher. Remember that we left stream ciphers before we talked about the math underlying AES last time. We covered stream ciphers. So AES is encrypting blocks of 128 bits. 128 bits are 16 bytes, so blocks of 16 bytes are encrypted, which doesn't seem to be a whole lot. So there are different choices for the key that you could use, the key length. So 128 bits is the most common one, key length of 128 bits. And for more secure applications, we have choices of 192 or 256 bits as well. So the AES is being run in rounds. I touched on that already above. So the same set of actions is being run on a certain state. So originally you have the plain text, then it's going to be run through round one, and that gives you some what is called state. So it's not the ciphertext yet, but it's not the plain text yet either. So it's somewhere in between, and that state is changed several times by running more and more rounds. Okay, until in the last round you actually do get the ciphertext. Needless to say, in decryption you will have to reverse all that. So it's a symmetric cipher. So basically what you do is you encrypt, and then for decryption you reverse all what you did in encryption. So the number of rounds depends on the key length. The most common one that we are going to cover here is a key length of 128, and this is 10 rounds. Okay, 10 rounds for 128 bits. So for higher security applications, you have longer key lengths and a higher number of rounds also. So at this time, AES is considered very, very, very strong. So it's the most important symmetric cipher in the world. And even the NSA allows AES for classified information up to top secret. And you may or may not know that, but top secret is the highest security classification that the US government actually has. So of course they choose higher key lengths, you know, but it is pretty secure. So what is the structure of AES? As we already said, AES encrypts blocks of 120 bits each round, which is 16 bytes. So what you see here is the overview picture of what these rounds look like. So what you see here is round one, and you see the second to last round here, and then the final round here, and altogether we have 10 of those. And all of these rounds have the very same structure, the very same things that are being done to the state. So convince yourself that in between two rounds, we have an intermediate result, which leads us from the original plain text to the ciphertext. And in between two rounds, you have what is called that state. That state represents, something in between ciphertext and plain text and ciphertext. It's not plain text anymore, but it's not ciphertext already either. It's somewhere in between. It's the result of, whatever data you get between two rounds. So that said, what does a round look like? So like here, a typical round, okay? And in 128-bit key lengths, we have 10 rounds, and 8 of these rounds are absolutely identical. And we are going to say what the difference is in these other two rounds, which is the first and the very last round, what those differences are compared to a regular round. So each round has 4 layers. Whoops. 4 layers for each round. So the first layer is what is called the byte substitution. Byte substitution provides for confusion. And you may remember in the second, in the introductory lecture, in the second part of it, we talked about confusion and diffusion. So the confusion here tries to make the relationship between the input, originally the plain text, and the output, which is some state, as complex as possible. And remember, we are applying 10 rounds of this stuff. So, which means that with each round, we make, that relationship more and more complex. So the next two rounds are shift row and mixed column. Those provide for diffusion. So here again, you learned in the introductory lecture, diffusion is for actually spreading out those changes at the bit level across all of the bits of the ciphertext. So if I change just one bit in the whole block of 128 bits, that means, in general, it's being expected that at least 50% of the output bits change across all of the output bits. All of the output bits. So this is what the diffusion is. Okay, we diffuse the changes over all of the output bits. So, and finally, of course, we need to make our permutations depending on the key. This is key, so to speak, pun intended. So the last layer of these 4 layers is the key addition. And when we say addition in cryptography, what we really mean is, addition mod 2 or XOR or whatever way you think about that operation. And we talked about it, in detail before. So those are the general 4 layers that each of these rounds has, specifically 8 rounds. But there is a little bit of a difference for the very first round and the very last round. So let's talk about the very first one. So what you see here in the very first, you see it also is our regular 4-layer round. So it's identical basically to what we had before, what we just discussed. Okay, however, There is a difference. We have an additional key addition layer. So you see, by the end of a regular round, we add the key. And here, what is being done in the very beginning, we have an additional um, key addition layers. So what we do here is actually to add the key. Okay. Again, and this is in addition, to each of the key addition layers. So if we have 10 rounds altogether, what that means is that we have a key addition layer at every round. And then we have one additional one in the very beginning, which basically means that we, instead of having 10 sets of keys, we have to have 11, one additional uh, set of keys. So the sub key is added at the beginning and the end, and specifically the beginning is kind of in addition. And this is what is called key whitening. This is called key whitening. Okay. So what's the other difference? I said the beginning is different, and the very first round and the very last round. At the very last round, what you see here is comparing to here that we do not have a mixed column layer. Okay, this is missing here. We have the byte substitution layer, we have the shift rows layer, and we have the key addition layer, but this guy here is missing in the last round. Okay. All right, so those are the differences. Um, Otherwise, you see that these four layers in each round are pretty homogeneous, not much to be surprised at. So what we're going to do is we are going to look into how a typical round, in a warm up phase in between the first and the last one, how this is being run. So how encryption is being done in these four layers. So by the way, I talked about the set of keys. So originally, of course, we have just one key of 128 bits here in our case. It could be more for higher security, as we learned, 192 or 256. Um, so you see that we add a key 11 times. So the truth is that we have one original key, which is 128 bits, and we generate. So, and this original key is going to be added here in the very first round. And then all of these other keys, so here in the first round, before the first round actually, and all of these other keys, and of course many in between here, um, those are different keys. Those are a different set of 128 bits each time by the end of each round. So the question is, where do all these keys come from? Well, they also follow a well-defined algorithm, which is called a key schedule. So what that means is that we are going to generate out of the original key, we are going to generate another 10 different keys that are going to be applied at each round. Okay, so not a big deal, but you have to know that our original key is only being applied once. Otherwise, it is being used as the basis to generate another set of 10 keys. Alrighty, so, and this is going to be, talked about, we are going to cover that in its own section, which is called key schedule. So that said, now we are going to dive in what a typical round looks like. Okay, so this is the exploded version of, let me change that, the exploded version of one round. Okay, so what I said is that the byte substitution here is providing for confusion. So confusion is being um, implemented by running through what is called an S box, a substitution box. Okay, so we have um, 16 substitution boxes that are all the same. So each byte of the 16 input bytes to a certain round are going to be run through the same S box. Okay, so the S box is pre-computed, and we are going to look into it in a second. It's already the application of what we learned about Galois fields. So this is the confusion part. And then we shift the order of bytes and we spread them. See, for instance, those 4 bytes, they are being spread, all over the place, um, you know, um, over the output bytes of this round. So this is interesting, and it provides for diffusion. And it's specifically this first part here, it provides for diffusion at the byte level. And the other part, the mixed column part, is providing diffusion at the bit level. So first we spread the different bytes all across the 16 bytes, and then we further diffuse it by diffusing the bits within those, packs of 4 bytes. So that's how the diffusion part works. Okay, all right. So finally, we have the key addition, of course. This we have at the end of every round, um, homogeneously, the same thing over and over again. Okay, so we we now talk about these different layers in the order as they appear here. Except for the key addition layer, there's not much to be said. We only need to learn here where the keys are coming from and how they are generated. But the operation itself is pretty primitive. It's just a plain old XOR that by now we are all familiar with. Okay, so let's start with the byte substitution. And again, this provides for confusion. So it makes the input-output relationship of the data for one round, and it's going to be repeated 10 times. It makes that relationship as complex as possible. So what you see here, the S here is actually that substitution box transformation of an input AI of X, and this is going to be transformed into an output BI of X. So, and the I actually stands for the number of the byte. Okay, so the substitution layer acts on bytes. So all 16 X boxes, as I already said, are the same. Okay, so how are these bytes transformed and where does Galois come into play? Well, right here. So transforming the bytes, we come in with our 16 bits and take bytes, sorry, and look at each byte individually. So we have 8 bits here, and the first step is a Galois field 2 to the 8 inverse. So remember that Galois field 2 to the 8 is an extension field, so everything works on polynomials. And remember that the polynomial has to be specified because if you compute inverses in the extension fields, those inverses really depend on the kind of primitive, non-reducible polynomial, um, and that needs to be standardized. And it is, sorry for taking that away again, it is this polynomial, this primitive polynomial for AES. So this is part of the standard. So given that polynomial, we compute for each byte, we compute the inverse in Galois field 2 to the 8. Okay. So this provides 16 bytes, which we call B prime, and the I again stands for the byte number. And again, we have the dependency on X here. Those are all polynomial operations. So we with that transformation of, A inverse, what we get is that B prime out here. Okay, so B prime now is going to be fed into a affine mapping. And that affine mapping is also standardized, and we're going to look into it in a second. And what the affine mapping is for, it confuses the strict mathematical structure that we had here in our Galois field inverse. Okay, so it further confuses and makes that relationship between an input, and an output byte more complex, or even more complex, I should say. Okay, so in other words, we have two steps. We have the inverse and we have the affine mapping. Okay, so this is what I just said. The S box is an inversion box plus an affine mapping. So in reality, the S box really is pre-computed. So you have these two operations here. You have these two operations, all pre-computed. Because in the end, there are only 256 different options. Okay, and you can put that into a matrix that can be easily looked up. So, as an example, let's look at an example. Let's say that some AI is this. Okay, 8 bits. The hex representation is that. Okay, so we get the inverse of this. So for your convenience, what I did is I provided the inversion box, which is again the first step of the S box. I provided the inversion box here. So what we had D1. So the inversion for Galois field 2 to the 8 of that byte. And remember, again, those are all polynomial operations is 0, 7. So, but having the chance to actually look it up makes it so much easier, of course. But you can actually do the math and you will find that for an AI of D1, we get an inverse of that, which is 0, 7. Okay, 0, 7. So this is the first step. This is the first step, the inversion step. Now comes the affine mapping step that diffuses that mathematical structure, um, basically destroys that mathematical structure so that an attacker cannot strictly rely on the Galois field 2 to the 8 inversion. So what's happening here is that you have a standard matrix, which is part of the standard, and you transform a byte. So you see the different bits here. Okay, 8 bits of B prime. This is this here. Okay, you see those, and they're going to be multiplied with this standard matrix. So an affine mapping is actually multiplication plus a constant. And after the multiplication, you add this constant, again, a set of bits, mod 2. So this is the affine mapping step. And what you get is now you get an output byte. And this is the result of the substitution layer here. Okay. All right. So when you do that operation here in our example, you get this result. So B prime is mapped in an affine mapping to BI. And in this case, the concrete result is what you see here. Okay. So here, for your convenience, I provide the inversion box. And remember that inversion box plus affine mapping is what makes up the S box. So all of these relatively seemingly complicated steps can just be looked up conveniently by splitting a byte into an X component, the first 4 bits, and a Y component, which is the, up here, and you just look up the result wherever these two meet. Okay, so this is what's being done here. And this S box, is in the textbook and it can be looked up online. It's not a secret. Okay, so now we get into diffusion. The first step was confusion, and the second step is the first part of diffusion. So we have 2 parts of diffusion. The first part is shift row, which provides diffusion at the byte level. Okay, so why is it called shift rows? Because we actually do shift rows. And we will understand that in a second. And the second step is the mixed columns, which provides diffusion at the bit level. At the level of 4 bytes that before got diffused at the byte level. So we do not have consecutive bytes anymore. Okay, you see that here in this example. So let's talk about that first step of diffusion, which provides diffusion at the byte level again. So why is it called shift rows? Well, what you see here is that the different bytes, and we have 16 bytes of input at each round, they are being assembled in a 4x4 square. So what you see at each row of that square, we have already like, a different assembly of bytes to begin with. And now in this matrix, if you want, we shift to the left. And the second row, we don't shift the first row. In the second row, we shift by 1 byte to the left. In the third row, we shift by 2 bytes to the left. And in the third row, we shift by 3 bytes to the left. So we get a totally different set of bytes now. Okay, so for instance, the first quadruple of bytes looks like that. And you see, I use that as an example here in the mixed columns layer. And like the last set of 4 bytes is B12, B1, B6, B11. So just check it out. In our prior uh, prior schematic, what we get here in the last quadruple of bytes. So those are 4 bytes. They're just not named. Um, you see where they come from. We have B12 here. We have B1 here, and so forth. Okay. So you see that this input here got totally confused at the byte level. So the sequence of bytes has been seriously disturbed. Okay. And you see what I just demonstrated and set here on the schematic. Um, you see here that last set of bytes. Oops, sorry. It's just that set of bytes that I showed you in the schematic above. Okay, as an illustration. So in other words, this matrix here is being expanded again. So the first 4 bytes, is this, B0, B5, B10, B15, and the second, is that. So just imagine that you kind of put that flat off the ground again, each of these 4 bytes, and this is the resulting order of these bytes again. Okay. So now what we do is we do mixed columns. So that set of bytes that got, diffused in the prior step, we are now going to diffuse at the bit level. So the mixed column layer is actually again, polynomial transformation that happens in Galois field 2 to the 8. Okay. So remember, it has to do with polynomial reduction. So if I do not have a mod here, this is because it's understood that we do the modular reduction because it's an extension field. We do that by applying the primitive polynomial, which is the standard for AES. So now we have these bytes here, and we multiply them with this standardized matrix, and we get a set of another 4 bytes out of that, which is the output at that level. And the C sequence of bits, remember, is this part here that goes into the key addition layer, where we basically just add the key, XOR the key to all of these bytes. Okay, let me clean up the mess here. So here's an example. When you see these numbers here, 01, 02, 03, what these really are, they are polynomials in our Galois field, in our extension field. Okay. So, for instance, for computing C0, for example, what we do here is we multiply these 4 bytes with these 4 numbers. So the first step, for instance, is to have B0 being multiplied with O2. Okay, so B0 times O2. So C0 is B0 times O2 plus B5 times O3 plus B10 times O1 plus B15 times O1. Okay, so this results in this equation for just C0. And then, of course, you have C1, C2, and C3. And all of these are polynomial operations. And at the end, you have to reduce whatever comes out of this with our primitive polynomial, with our non-reducible polynomial, which basically takes the place of a prime number in an extension field. So convince yourself that this diffuses the bits, all of the bits of these bytes that got thrown together here in the prior step. Remember that the order of these bytes got seriously diffused. So this further diffuses the information at the bit level. So that's how we actually get the result that just changing a single bit results in at least 50% of the output bits being changed all across the bits, okay? Not just concentrated in one spot, but statistically spread all over the output bits. Okay, so this was basically it for the encryption. The next step is to understand how the keys are being computed. So what is the key schedule? And we need to understand that because in the last step, remember, we add our key here with a simple XOR. So this is very, very primitive, of course. So that would be the last step after, we looked into the details of, the 3 more complicated actions in one round. So I will stop right here. because this is part of the second part of the lecture, um, which is going to cover the key schedule as well as decryption. So thank you very much for chiming in and for listening. I hope it clarified how encryption is being done, and I see you in the second part.